I hope so. Then there was this under initiative, and just monitor the I don't think there was okay. Let's throw this view first. How was the meeting?
Oh, was it?
Oh, okay. Oh, I see. It's just in front of the conference later.
Yes, all right. So, this is our last science session, but there's no other. Is there anybody who did not come as part of that last chance?
Yeah. Art for fluoride.
For fluoride.
Okay. Well, I think we can start. So welcome today. Welcome to our last science session today. It's going to be about plant formation. And we'll start with a remote talk from Jane about ALMA observations of the T-Tauri star Dr Tau. Yeah. So, have you already shared? Let's see. Have you shared your screen?
In principle, yes. I see sharing on my screen.
This one? Yeah, okay, I have got it. Okay, it's great. Okay, we can go.
Okay, so everyone sees my screen and they can hear me? Okay, great. Hi, everyone. I'm Jane Huang. I'm a third-year Sagan Fellow at University of Michigan. Before I start, I'd like to thank the SOC for all their hard work in putting this symposium together, as well as the program leads for a great fellowship experience. In the past decade, high-resolution millimeter continuum imaging of protoplanetary disks has shown us that many of them exhibit very intricate, well-organized dust substructures on scales of 10 AU or less. These substructures have generally been interpreted as evidence that planet formation is already advanced and widespread within the first few million years of a disk lifetime. Meanwhile, scattered light imaging and molecular imaging of disks have revealed unexpected complexity in their environments on scales of tens to thousands of AU. And these observations suggest that planet formation can be rather more chaotic than typically assumed. This talk will focus on one such system, Dr Tau. Dr Tau is a roughly solar mass pre-main sequence star in the Taurus star-forming region. From its spectral energy distribution, it's categorized as a class 2 young stellar object, meaning that it's supposed to be more evolved and has shed its envelope. It is most notable for long-term dimming and brightening events that have been tracked over the 20th century. The most extreme one being an increase in its brightness by 5 magnitudes in the 1970s, as shown in this light curve on the right. This extreme brightening event has drawn comparisons to the outbursts of the young embedded FU-ORI systems. The FU-ORI outbursts have been ascribed to some sort of interaction with the environment, such as stellar flybys, binary interactions, and infall-driven disk instabilities. And these images on the right-hand side of the slide show the various kinds of complex environments that have been observed toward FU-ORI type systems. So even though Dr Tau is not an FU-ORI system, its extreme brightness changes made me curious about what its environment looked like. Uh-oh. Oh no. Sorry about this. Okay. Although Dr Tau has been one of the most extensively studied pre-main sequence stars, spatially resolved imaging has been surprisingly scarce. Recently, Mesa et al. Imaged Dr Tau in scattered light with SPHERE and found a nice set of spiral structures, and they considered possible explanations for what was responsible for these spirals. They looked at Gaia data and concluded that it was unlikely that Dr Tau underwent a close encounter recently with another star. Their high contrast imaging ruled out a companion more than several Jupiter masses beyond 50 AU from the star. And they also thought that gravitational instability was unlikely because the disk mass is not that large. So they suggested instead that infalling material could be responsible for triggering the arms. Now, in the scattered light image, you don't actually see evidence for an envelope or other infalling material. However, our new CO interferometric observations do in fact reveal complex extended emission around dr tau. The second row shows the optically thinner C18 emission, which traces a material closer to the star, that is, the Keplerian circumstellar disk. And you can see that the Keplerian disk is rather more compact than the extended material traced by 12CO. So here 12CO looks a bit of a mess because it's been integrated over all velocities where emission is seen, but the individual components become more legible when you break them down by the different velocity ranges. So just to orient you, dr tau has a systemic velocity of 9.9 kilometers per second, and we are looking at it such that the circumstellar disk is almost face-on to us. And here we don't really see the circumstellar disk itself due to the high optical depth of 12CO. At high velocity offsets from the systemic velocity, we see outflow emission. That's asymmetric. The blue shifted side appears to be more collimated, while the red shifted side manifests as an extended ring of material. And then close to the systemic velocity, we see an arm and envelope material. Notably, the CO arm is much more extended than the ones detected in scattered light. The scattered light arms are only seen out to about 200 AU, whereas the CO arm is detected out to about 1200 AU. And this really underlines the importance of obtaining molecular line observations for exploring the environments of planet-forming disks. The CO arm also shows a clump, which is interesting in light of dr tau's extreme brightness changes because simulations have suggested that migration of clumps onto young stars can drive outbursts. However, one important caveat is that these simulations have been run for disks that are younger and much more massive than dr tau. So it's a question of whether such mechanisms can operate in more evolved, modestly sized systems. Not only does dr tau exhibit unusual structures, but it also exhibits a peculiar chemistry. We obtained a strong detection of sulfur monoxide, which has otherwise rarely been detected in Class II protoplanetary disks. And this paucity of sulfur monoxide observations has been attributed to the gas phase C/O ratio being higher than 1. And that's because when the C/O ratio tips over 1, the production of carbon monosulfide, or CS, is favored over the production of sulfur monoxide. Thus, conversely, the strong detection of sulfur monoxide in dr tau hints that it has a lower gas phase C/O ratio than most disks studied so far. If that is the case, then we should expect to see the lower C/O ratio imprinted on other molecules. And another key molecule for tracing the gas phase C/O ratio is C2H, which is also seen to be very bright in other disks, and it's been tied likewise to elevated gas phase C/O ratios, as shown in these comparisons of 2019. Along similar lines, HCN production is expected to be enhanced when gas phase C/O ratios are higher because its formation depends on hydrocarbons as a starting point. So we obtain new observations of C2H and HCN towards dr tau. And here we plot dr tau's properties against the plots from Miatello et al. 2019, assuming different overall levels of C/O depletion. And in general, you see that the dr tau's flux is lower than the other sources. And it seems to be consistent, again, with a lower gas phase C/O ratio. We can also see a striking contrast in dr tau's behavior with other disks when we look at the spectra of C18O, HCN, and C2H on the left for dr tau, and then on the right for a disk survey from Pegues et al. 2021. With dr tau, we get very, very bright C18O emission and faint HCN and C2H emission. And then this is flipped around for other disks where the C2H and HCN emission are considerably brighter than C18O. So why do we care about the C/O ratios of disks? It's because disks provide the starting material for planet formation. So the atmospheric composition of planets is believed to depend on the C/O ratio of the surrounding disk material at the time of formation. So in principle, as illustrated in this figure from Moliere et al. 2022, if you can measure the C/O ratio of the planetary atmosphere and you compare it to disk models, then you can backtrace where the planet must have formed. But this method requires good observational constraints on the C/O ratio behavior of disks. As for why dr tau C/O ratio seems to differ from many other disks, this is not so straightforward to answer. One major source of uncertainty is how old dr tau is. In general, for pre-main sequence stars, ages are already uncertain as it is, but dr tau stellar properties have been particularly difficult to constrain due both to significant continuum veiling and disagreements over the level of foreground extinction. Seeing an envelope around dr tau might suggest that the younger end of the age range is more likely, in which case the lower C/O ratio would be an indication that it has just had less time to undergo chemical processing compared to the other disks that have been observed. This would imply that C/O ratios can evolve very, very rapidly in disks, which would mean that tying atmospheric compositions to disk compositions would require a very precise knowledge of the timing of planet formation, which we don't yet have. But other observations are now suggesting that it's possible that older systems are either retaining their primordial envelopes for much of their life, or it's possible that later on in life they can acquire secondary envelopes. So the complex structures that we're seeing associated with dr tau do not necessarily guarantee that it's younger than most other class 2 disks. And if indeed dr tau is indeed on the older end of the age range estimates that have been produced, it could be that there is naturally a wide diversity in C/O ratios at a given disk age, which also introduces complexity to the concept of comparing atmospheric ratios to disk ratios. So to summarize, our sensitive CO observations of dr tau have shown that it's associated with an envelope and asymmetric outflow and a large-scale spiral arm. These structures are reminiscent of those seen around younger embedded outbursting Fiore sources, suggesting that there could be some sort of common mechanism driving their extreme stellar activity, such as infall-driven disk instabilities. We see bright SO emission and faint C2H and HCN emission, which is in stark contrast to what's typically been observed in disks so far. These line observations suggest that the gas phase C/O ratio is probably lower than most other disks that have been observed so far. And this therefore makes dr tau an important data point for understanding both the chemical diversity of disks and for constraining models for inferring the origins of exoplanets. Thank you for your attention, and I'm happy to take questions.
Questions in the audience? Are there any questions online? I don't know. No? Okay. So what's the driving cause for the main difference in the scattered light image than the CO image that you from ALMA? Because the sizes are really different.
Well, with scattered light, sorry, I hear some weird echoing. So there are two general factors. One is that in general, scattered light is not that sensitive, especially on the ground, to structures at large distances because the starlight gets diluted. The other is that if there's some material close to, if there's some shadowing, then even if you have a lot of material large distances, it's not intercepting starlight, so then it won't scatter. Whereas, with molecular emission, it's the molecules themselves that are emitting radiation. So as long as you have enough material out there, you can see its emission. A third factor, which I think is less likely but should be considered, is that the dust to gas ratio is changing. But I think that's less likely than the other two explanations.
If there are no more questions, then let's thank Jane again. And we'll go to the next talk of today.
Can you hear me okay? Great.
Oh, just.
Are the slides?